Good afternoon, ladies and gentlemen. I'm going to talk to you today about some of the simulation modeling that I did for my thesis. And we're going to look at assessing a novel tailings dewatering technology using the simulation model that I had developed. So we're all here to talk about tailings, and we know how it's an interrelated complex system of all kinds of different pathways and processes and technologies. At the last conference, we heard about the tailings technology roadmap. There's hundreds of different technologies and variations that were looked at, and these technologies were purpose-built for oil sands. They were adopted from other industries. They're bench scale, pilot scale, they're academic experiments, or even thought experiments or ideas that people had. And the background of these technology vendors range from people right in the oil sands industry to other mining industries to other industries completely, or small business entrepreneurs that don't have a lot of understanding of oil sands, but they know their dewatering technology really well. So there's a big range of technologies and background in the vendors. And we heard about the technology roadmap last year that looked at trying to understand and evaluate these technologies and see how they might fit within a mine plan and develop. They developed and laid a good groundwork for assessing these technologies and taking a snapshot in time, if you will. But these technologies are constantly being developed and are evolving. And I'm sure Jonathan and Phil get a phone call every other day of a new technology vendor that has a new technology they want to apply to the oil sands. And so that was what one of the objectives, or the objective of my thesis, is to help come up with an assessment tool that can aid in trying to understand these different technologies, try and help these new technologies and how they might apply to a mine plan, and look at their strengths and weaknesses and help guide the next stage of development and where you should put your resources to advance that technology. So in the past couple of conferences, I talked about the development of the model and the validation, so I'm going to skip over that. You can look to the past papers for more information. What I'm going to talk to you today is we took that model, the TMSim, and evaluated a novel technology, Crosswell filtration. And Al Hyman referred to that a little bit earlier this morning. It's a technology that we developed at OSTRF, myself and Chenzi Zhang, a master's student. And Crosswell filtration is a filtration process where your suspension, your tailings, is flowing in a pipeline parallel to your filtration media. And because of that Crosswell filtration, it's eroding the cake, and you're maintaining an equilibrium cake thickness, and that allows to maintain a filtration rate much longer than conventional dead-end filtration. And so our idea of how to apply that to a mine plan is we would take whole tailings from the extraction plant at 50-55% weight solids and pass that through the Crosswell filtration system, extract the water from the tailings, and make sure we extract sufficient water so that coming out of the end of our process, we have a non-segregating tailings deposit, so we got to be in the 70-75% weight solids range. And we can deposit that material within pit, and if the density is high enough, we can start to stack that material. And so we're not generating any more mature fine tailings or fluid fine tailings. We can also recycle that water immediately back from our whole tailings that we've filtered back to the extraction process. And by dewatering the tailings right out of extraction, we're also recycling heat from those tailings that we can then use in the extraction process, and that helps to reduce the greenhouse gases associated with heating the tailings, the process water. So based on this process diagram, we're going to run the tailings management simulation. So the first step was to develop a dewatering model to represent the Crosswell filtration. So the work that I did and Chenzi did is we kind of took a shotgun blast of different tailings, different dewatering, or different filter media, and different operating conditions. And we weren't really looking at optimizing back then, but we found at the same time CanMet was doing some filtration work on flocculated and unflocculated tailings. And we see our data fits nicely with their unflocculated filtration data So for the dewatering model, we're going to use the CanMet unflocculated tailings data. And so now, to develop the dewatering model, I calculated an equivalent cake permeability, and I used that to estimate the filtration surface area that we needed for our Crosswell filtration process. And when you take into account the properties of our tailings and the filter medium, the original work that we did, we were just sort of trying to see if it would work. We weren't really working on optimizing the process, but if we were to calculate the surface area that we need for that low permeability, it would be like 60,000 square meters. So it's unfeasible at that filtration rate. But we see if with improvements just in our operating conditions, we can increase that equivalent permeability at least an order of magnitude, if not more, by optimizing our pressures and our flow rates and our cake thicknesses. But even at that equivalent permeability, we're still in the 10,000 square meter range or slightly higher. It's probably not feasible at that range. And for lack of data as well, we're going to look at potentially you might have to actually flock the tailings to improve your filterability of your tailings. So for the dewatering model, I'm actually going to use that flocculated tailings filtration data. So using that model, I ran the tailings simulation, and we specified that our target solids content coming out the end of our Crosswell filtration would be 75% solids. And so the model, what you see on this axis is the required filter surface area. So if we look at that dashed line, this is whole tailings being filtered, and we can see that required surface area ranges from like 1,500 square meters to over 4,000 square meters. So it's a huge range. So what that means, if you have a static system, half the time you're under dewatering your tailings, your product coming out is going to have low solids content, it's still going to segregate. The other half of the time you're over dewatering, potentially you could plug your filters off, or you're wasting energy because you're dewatering more than you actually need to. So some of the causes for those large fluctuations was the variability in the fines content and the feed flow rate into the system. So we thought if we could, the fines content of the whole tailings, or the sand to fines ratio, was above 5. So we thought if we could spike accumulated MFT that was on site into the whole tailings before we filtered it, we could balance out these two solid lines here, we could balance out the required surface area. So now if you have a static system at about 3,000 or 3,500 square meters, you don't have as much variation. So that's what we did for the next simulation, is we incorporated spiking at the sand to fines ratio of 4.5 to 1. There's also variations in the flow rate going into the system. So if you have a static system and a static number of pipes, if your flow rate is too low, your velocity is going to be a lot lower, so your cake thickness builds up, so your filtration rate drops. And in worst case scenario, if your filtration rate is too low, that bottom line, you're barely dewatering your tailings, and you're getting segregating product out of the end, and you're forming beach and having that thin fine tailings running off. And so through the modeling, we decided we needed to stabilize that flow rate, so we incorporated a feedback loop. So we take the dewatered tailings and some filtrate and stabilize that feed flow rate, and we find that we can get a much more stabilized product coming out the end of our Crosswell filtration process. So then the next stage of the modeling, we have a spiking of MFT, we have recycling of the dewatered tailings, and we find that we can generate a tailings deposition plan that works well with the mining plan. So we have sufficient space in pit so that the mining is advancing sufficiently ahead. We have room to build our impoundments. We have sufficient overburden to construct our containment. So this successful model, we had 1.7 billion cubic meters of Crosswell filtration tailings deposited back into the pit. We were able to consume about 100 million cubic meters of MFT through the spiking process, so all the MFT that was on this model mine plan site. And we maintained our stockpile of process water at about 40 million cubic meters. And so the process water demand for the model mine plan that I used was about 100 million cubic meters per year, and we could see the Crosswell filtration process can satisfy at least 2/3 of that recycled water. And so remember, that water is coming from the warm tailings, so we're recycling heat with that 2/3 of the filtrate. A quarter of that processed water had to be made up from pond water, so that's from runoff and from seepage or consolidation water from the deposit. And only about 4 to 5 million cubic meters per year had to be made up from off-site sources. And the model also provides information on deposit density profiles with time. So this chart shows you solids content profile at the end of filling and with time. And we see after about 5 to 10 years, most of the dewatering was complete. We also have effective stress profiles and pore pressure profiles, and after 30 years, we have almost 100% dissipation of pore pressure. So the model provides the ability to compare the effective stress profiles and density profiles, so we can start to compare different scenarios and how well your deposit is actually going to behave. And so these two results, or the results I showed you on the presentation, are some of the later case studies that I've completed. The results in the paper are some of the more preliminary work that I did, so you'll see some differences in the data. And this case here was one of the best case scenarios for our deposit behavior, but it provides us a target of where we want to be. If we want to have a successful deposit, our material behavior needs to behave like this to be successful. So in conclusion, Crosswell filtration, why do we care about this technology? It has the potential to provide a high density stackable deposit you can place back in pit. You're preventing the future accumulation of fluid fine tailings. You actually have the potential as well to spike the mature fine tailings into your feed tailings before you dewater it, so you can consume tailings that you have on site. And 2/3 of the processed water that you get from the filtration process you can recycle back to your extraction plant, and that water is warm to hot, so you can start to recycle that heat back to your extraction process. And so the tailings management simulation modeling exercise, so right from the start of developing that dewatering model, that whole process of figuring out your parameters, your material deposit behaviors, identified some targets that we needed. So we saw in our dewatering process, some of the work that we have published so far, we're not quite where we need to be, so we have a target dewatering curve. We also came up with some improvements on the design to have the spiking and the feedback process to stabilize our filtration rates. And with the deposit behaviors, we have information and targets on what we actually need to have a successful tailings plan. For every one successful simulation that I ran, I probably had 10 that had failed because the material segregated, or there wasn't sufficient dewatering rates in the filtration process, and the material, when it was deposited, segregated, or it filled up the impoundment too quickly. So there was a lot of simulations that were run, and they all of those results combined can be used to help guide the next stage of research. We have targets now, what we need that dewatering rate to be, and targets for deposit behavior. I'd like to thank my supervisors and OSCR for funding, and TMSim and FS Consol for software support. Thank you.
Thank you, Nicholas. We've got some time for some questions. Any questions for Nicholas?
So Nick, just a question about your model. How open is this for people to take and actually use it for evaluating other technologies? How easy is it to change the different parameters to vary consolidation, slope, flocculation parameters, etc.?
So I tried to make it as generic as possible. There's a lot of so the input is a spreadsheet, and so you could put in ranges. A lot of the simulations I did here were deterministic, but you can put in probabilistic distributions. I didn't. I just did deterministic, but it has that opportunity for it. But you all of the inputs, I don't have a picture of that here, but there's hundreds of inputs that you can change and modify.
Do you have defaults that people can use if you don't have?
Yeah, in my thesis I have a model mine plan and data for default, and then you can change that as you need. Yeah, and GoldSim is to be able to change the model, the actual equations. You have to have the GoldSim software, but GoldSim makes a player file that I could give to someone that you could just hit run. So if you change all your inputs in the spreadsheet, whatever you want, and then hit run on the player file, it'll work. But FS Consol, the consolidation engine, is proprietary. So we're working on incorporating it all into a package that we could send out, and people can just change the inputs.
Dave Watula from McMaster University. I'm not at all familiar with this technology that you described, so I was wondering if you could comment on the properties of the actual filter media. I don't know what it is you're using, perhaps some sort of some metrics like pore size or porosity or anything like that, just to give a better sense of what's actually the filter media.
Yeah. So in the lab, we took, we started off with just water well screen, 2-inch pipe, slotted pipe. So they were up to 200 micron slots. So the standard monitoring well you'd use for geotechnical well slots. That's what we started with. And
Nothing else on top?
nope, just the pipe. And then the coarse fraction bridges across those openings, and it's actually the tailings themselves that are doing the filtering. That pipe is just there to support a structure for the sand particles and the cake. We did some tests where we had really fine pore space on the pipes, and we had lower dewatering rates compared to the really high pore space. So it's actually the tailings themselves, that cake, that acts as the filter media.
Thank you.
There's one right there. There we go.
What's the impact of bitumen in the slurry on this dewatering digest of the filtration?
That's still under investigation, but the CanMet data that they did on filterability, I can't recall the bitumen content off the top of my head, but was going to look to that paper to try and get an estimate of what that could do. But the cake that you develop is constantly being sheared, so the particles are being deposited and picked up and sheared. So if your filter media, if the pore spaces are large enough, it's just there to allow particles to bridge over it. So the bitumen might flow through those pore spaces. So this cake is a dynamic cake. So you're depositing particles and they're being sheared and picked up. So I don't think it's going to have a huge influence, but I guess the short answer is we still don't know exactly. That's still under investigation.
I have a question actually for you.
Yeah.
On this pipe, when it goes and you actually get the slurry to being deposited, was that a fairly constant solids content, or would it vary with time? Or did you know what it was ahead of time, or how did you account for that? Because then you'd have to adjust your compression curve up and down to account for your initial solids content at the end of this pipe, right?
So I think the design, you'd have density meters, and towards the end of your system you could have kickoffs. So once your tailings got to a certain density, you could discharge them earlier, a little bit earlier, or have them stay in a little bit longer so that you could try and maintain that final density at your target density.
Okay.
That's another question.
Hey Nick, just a question. When you do get it bundled together, maybe look, this is a suggestion, having a workshop or something. I know myself and some other folks who's in the individual member companies would be excited to use something like this and really see the full extent of its capabilities.
Yeah, for sure.
So what is the water quality of the filtration water? So what is the water quality?
It's the same chemistry of what's in the whole tailings that's going in. So whatever's coming out of the extraction plant, if our target was not to add chemicals, but you see the to get the dewatering rates that we needed, at least based on the data I had, we had to add flocculant. So the only thing we're changing is adding a flocculant to the water. So
How about the salt content and the suspended solids?
pardon?
Salt content. The salt.
Oh, all our tests were way less than 0.5%. Very little solids were in the filtrate. As soon as the cake formed, there was no fines that came out.
Okay, thank you so much, Nick, for your presentation.